Okay, so I was asked the following problem, June 2022, number 4. And this is there's two ways to do this. Um, I'll go over both ways. Um, but regardless, the idea is that you would want to basically say, well, you would hope that you can just interchange integrals and limits, but there's really no way to justify that. So in particular, what do I mean by that? 1 second. Yeah, so Fn of x. Sorry. All right, yeah. So you might think, well, maybe you could do use a dominator. So one thing is clear. Um, if x is in 0 to 1, then this here is going to be 0 because the denominator, well, I don't care what x is, the denominator is between 0 and 2. So in particular, the denominator is between 1 and 2. So the denominator is bigger or equal to 1. So this is less than or equal to this limit. And well, because x is between 0 and 1, this is 0. Okay. So yeah, maybe I should pop this in here. So certainly this limit almost everywhere is 0. And particularly 0 everywhere except 1. At 1, it's going to be n Fn of 1. So this is clearly just n over 2. So this goes as n goes to infinity. Well, that goes to infinity. So the point is, you might think, well, I can come up with a clever dominator and use dominant convergence theorem. You just can't. And the limit of the integral is going to be 1/2. So that proves you can't, because if you could come up with a dominator, the limit would be 0, not 0, it's 1/2. Okay. And the easy way to do this, and yeah, so the easy way to do this, and probably the best way to do this, is just do a u substitution. And do kind of the obvious u substitution, and just be careful. Yeah, so the idea of this problem is it's problem's pretty easy. But yeah, the idea is that you have to be careful and really justify interchanging limits and integrals. You might be tempted to use this fact that I'm circling in blue. Might be tempted to look at this and say, well, the limit for all x between 0 and 1 goes to 0, so the limit of the integrals should be 0, but it's not. All right, so what do we do? So I'm going to do a u substitution. U is going to be x the n. So first let's get x. X is u the 1 over n. Let me give myself plenty of room here. Yeah, so du n x to the n minus 1 dx. So that's going to be n x to the n dx times x to the minus 1. Well, what's x to the minus 1? U to the minus 1 over n. So u to the 1 over n du is the numerator, which gets rid of this pesky n. And of course, when x is 0, u is 0, and x is 1, u is 1. So, right, so this is going to be equal to the numerator here, nx to the n dx, is just u to the 1 over n du. And the denominator is 1 plus x cubed. So it's 1 plus u over n. Remember x is u to the 1 over n. And now you can use Donnelly convergence theorem. So in particular, u to the 1 over n is, well, this is less than or equal to, actually probably even have uniform convergence to 1/2, proving that's probably a pain. So let's use Donnelly convergence theorem kind of trivially. On 0 to 1, this is certainly less than or equal to 1. While this here, well, obviously is less than or equal to 1. So the whole integrand is bounded between, it's obviously not negative, so it's bounded between 0 and 1. So you use Donnelly convergence theorem. X to the n over 1 plus x cubed. So u to the 1 over n. All right, so pop the integral inside. It's u to the 0. This is kind of silly, right? But sorry, I forgot the du. So yeah, and this is, well, this is a constant 1/2. Integrate that over 0 to 1. 1/2. Yeah, so the other way to do this is, it's useful because yeah, I'm not sure of an example like this where you can't just do a u sub to basically solve it, but I'll definitely think about that and look for it, which makes the other way, the other idea where you estimate rather than just compute relevant. The kind of idea of what's going on here is breaking this integral up for very small epsilon. And the first integral, you have uniform convergence to 0. And notice, and this is the point, when epsilon is 0, this argument is just complete garbage because n goes to infinity as n goes to infinity. It doesn't go to 0 as n goes to infinity. It's because this here is strictly between, epsilon is really small, smaller than 1. This is what I circled is strictly between 0 and 1. So for fixed epsilon, this converges to 0. And so we have uniform convergence to 0. Right. So this is going to be equal to this limit. Right. Okay, but do kind of the similar thing. You have so this is less than this is let's see. Yeah, so I need to move this over. Okay, so this is x is less than or equal to 1, so this is less than or equal to 2. The basic idea is now the denominator is basically 2. No, 2. You can quantify that kind of trivially. So it's bigger or equal to 1 plus 1 minus epsilon cubed, just because this is a strictly increasing function. So, I mean, on the real line, it's strictly increasing, but it's yeah, so maybe that's 2. So this here, this is between, keep that. I'll go from left to right. So yeah, you take 1 over, it gets flipped. So it's 1/2. And basically the same thing. Yeah, and this you can compute. There's nothing really to it. That's just fundamental theorem. Uh, yeah, n plus 1 over n plus 1. 1 minus epsilon. Same kind of thing is going on. This is n over n plus 1. 1 minus. And because epsilon is positive, this goes to 1. Right. So, if you want to be really precise, it's a little tricky using lim sups and lim imps. I really wouldn't worry about this problem. The next prelim, or tomorrow's prelim. But this is the idea. So yeah, so star. Or really you could just use, yeah, you could use, well, yeah, you could use the squeeze. You can't really use the squeeze limit in, you know, by itself. I mean, I guess you probably could if you creatively instead of epsilon, do something like one over like 1/n or something like that. I have to check if you can do that. But as n goes to infinity, star is between well, because the limit of the integral is 1, so it's 1/2 and 1 over 1 plus cubed. Nothing special about epsilon. It's gotta be 1/2. Again, epsilon, the idea is really small.
We had a question about a proof you did in a previous session.
Yeah.
So it's if f and g are sequences that converge in measure, or if f and g converge in measure, then show that f times g converges in measure. Is there an easier way to do that that involves proving it for f squared and then like extrapolating that for f and g, for f times g?
Um,
Yeah, I think in class what you did was demonstrate you can express f times g as a function of or like a linear combination of f squared and g squared.
right. Let's see. Yeah, so Fn, right, Fn is going to be F. Um, yeah, okay. Yeah, so this is something you want to be careful of because so it's not true when you have a set of infinite measure. Trying to remember the counterexample. It's not necessarily true. But okay, what goes wrong? So y is squared, not necessarily. So you want this to go to FG. Certainly addition, no problem. I mean, okay.
Yeah, and I
I
think
mean,
this,
you could simplify. Yeah, you could probably do that. Simplify. Um, by proving squared, like a convergence measure for squared on a set of zero to a set of finite measure. So yeah, okay. Yeah, okay. So that's yeah, that would be fine. Yeah, okay. So this would converge and measure to FG. Right. yeah, just writing this to keep this in the recording. Yeah, because certainly if Fn goes to F in measure, Gn goes to G in measure, and you have convergence in measure of any two sequences of functions, the addition converges in measure also. So I'll even use Hn just so it's not confusing. If Hn goes to H, so really Hn is any of Hn is either Fn, Gn, or Fn plus Gn. That clear? And this is yeah, so we'll see. I mean, it should make this simpler, but yeah. Okay. Squared. So yeah, you do the same thing. You don't, there's no way to avoid that. Hn squared minus h squared. Well, all right, so there's really no adding and you really need to even add and subtract. Oops. Okay. Yeah, okay, you could do the same thing we did before, and I don't see how to avoid it. So yeah, so using that 6a,
If it's the same thing as before, then I don't want to make you go through that again.
yeah, so I don't see a way to, no, this does simplify it, definitely. But I don't think there's a way to like avoid adding and subtracting, which is fine. Uh, so you could write this as Hn. So this would be less than or equal to Hn squared. Yeah, and now you can, and the point is, yeah, off of this is bounded off of a tiny, a set of tiny measure, this is bounded by that 6a. And then you can basically, it's a little simpler working with this. we had a product in the video, Fn minus F times Gn minus G. That was kind of an annoying thing to work with. So yeah, you could do this. Makes it a little simpler. Yeah, that's a good idea. I mean, so this makes sense, kind of, but you would have to repeat the essentially the same arguments we did before. But it does make this a little, that definitely does make it simpler.
So you're basically done at that stage though, right? Because one of those is essentially if epsilon goes to 0, then epsilon squared also goes to 0. And then if the other side of that, the +2 magnitude hn minus h is essentially 2 times a finite number times epsilon also goes to 0 and you're done.
Well, no, just because remember what the goal is. For any eta bigger than 0. Okay, I'm gonna have to move this over, sorry. This time. So this limit here, measure of this. What is it? Yeah, so for any tiny eta, the measure of this goes to 0. So basically, this here is it's arbitrarily small, except on a really small set of measures. As we go further and further in the sequence, that set gets smaller and smaller and smaller. So it's basically almost on all of E, this is less than eta, less than or equal to eta. So,
Yeah, I'm on the same page. Thank you.
yeah. Yeah, it's so weird. It says you left, but anyway, that's weird. Yeah. But yeah, no, that was a good observation. Okay, so the next problem that was asked was August 2017, number 6, and this is actually in the book without any details whatsoever, which is fine because it's really just a computation. Okay, so construct a function that's an L2, but not an LP for any other P between 1 and infinity. Okay. So this shows you how rigid membership in LP is. You can be in one LP, but not be in any other LP whatsoever. Right. So yeah, so the example is as follows. So let's say f of x is, this is much easier to state from 0 to infinity, but you can just set everything to be 0 on minus infinity to 0. So the example given in the book, it's -1/2. The denominator 1 plus absolute value of ln of x. So let's do this. Yeah, let's say it's just 0 on minus infinity to 0. Because everything is 0 on minus infinity to 0, it's enough to show that f of x, f is an L2. But it's not in, let's, well, f is not an LP, 0 to infinity. For any other p. So first of all, clearly this is not an L infinity because this is not essentially bounded. It is sorry. So this doesn't really make sense at 0, so it's open 0 to infinity. Makes more sense. Yeah, so this is definitely yeah, not essentially bounded. Particularly as we go towards 0, this function blows up to infinity. So yeah, there is no essential upper bound for this function. You always this function, you can always find a set of positive measure where this function is larger than any number prescribed that you want. Okay. So yeah, there exists for any m bigger than 0, there exists let's say delta bigger than 0, where f of x bigger than m. Sorry. On 0 delta. Okay. So in particular, this here has positive measure. So yeah, there is no essential upper bound for this function. So it's not an L infinity. Okay, what about L2? So something to note. This itself is a piecewise function, kind of trivially. So ln of x is positive on 1 to infinity, or non-negative. It's ln of 1 is 0. So from 1 to infinity, this is going to be x, and this is actually really important. And ln of x is negative from 0 to 1, so absolute value of it is minus it. So it's x to the minus 1/2 over minus ln of x on 0 to 1. Okay. All right, so the L2 norm squared, so we don't have that 1/2 floating around, just less stuff to write. So it's 0 to infinity f squared. Okay, and this is going to be 0 to 1. Use this one here. 1 minus. Yeah, you're gonna do kind of the obvious U sub. So this is squared here. One to infinity. Same thing, except it's 1 plus L. Okay, either way, both same sub. U is ln of x. Not a whole lot here. Du is exactly the numerator. All right, so two things. U is minus infinity. Fx equals 0. Three things rather. U equals 0. X equals 1, and last but not least, U is plus infinity if x equals infinity. All right, so this becomes minus infinity. So 0 to 1 converts to minus infinity to 0. X and minus 1 dx is just du. So it's 1 minus u squared. Basically the same thing. Bigger. Yeah, 0 to infinity. And this trivially converges. Right. Yeah, just literally integrate this. So this is going to be let's see. So it goes from u u equals 0 u to minus infinity to u equals minus infinity, u equals 0. Same thing here. So except you get a minus, so that means it goes from infinity yeah, it goes from 0 to infinity. So it's 1 minus 0. So it's 2. So actually, the L2 norm is 2 to the 1/2 square root of 2. Okay, so now let's do the other part, and that's really not much harder. So the idea is when P is bigger than 2, the problem is going to be yeah, when P is bigger than 2, the problem is going to be the 1 minus ln of x on 0 to no, the problem is going to be the numerator for P bigger than 2. For P less than 2, the problem in both of these, sorry, is going to be the numerator. But when P is bigger than 2, the problem is going to be this numerator on 0 to 1. When P is between 1 and infinity, the problem is going to be this numerator here. Right. So let's see why that is. All right, yeah, so let's do P is 2 here. Sorry, P bigger than 2. So when I do P bigger than 2, yeah, I'm just gonna integrate from 0 to 1. In particular, I want to show this as infinity, so I can just throw away the 1 to infinity part. Everything's not negative. So if I can prove this is infinity, then I'm good to go. So you take this here to the P, x and minus P over 2, and basically do the same thing. Okay, so U is ln of x. Du is x and minus 1 dx. So let's get x and minus P over 2 dx. And things look a little funky, but that's all right. So I'll just put a bar here. So yeah, x, that means x is e to the u. Yeah, this example is going to show it's pretty dramatic how badly it fails to be in LP, both cases. I think the easiest way to do this, it's x to the minus 1 dx times x to the 1 minus P over 2. You just minus 1 gives you minus P over 2. So what is this? Well, that's just du. And so this one here is just e to the 1 minus P over 2 times u. Okay, so it's getting a little crowded here. So let me do this. Yeah, so yeah, this is going to be equal to, and here's one of the key things. Just like before, the integral is going to be converted to minus infinity to 0. So it's e to the 1 minus P over 2u over 1 minus u P. Just replace u with ln of x. And if the fact that this is negative makes things all confusing, we could just do a trivial substitution. Let's say v is minus u. So that converts things from 0 to infinity. So it would technically go from infinity to 0, but dv is minus du. So it's minus u. U is minus v, so it's going to be P over 2 minus 1. And this definitely, I think, makes things much clearer. Okay, so the key thing here is, well, What do we know about this? P is bigger than 2. So this is bigger than 0. Okay, so what I want to do, and there's a million different, probably a lot of different ways to do this. We got to show that this is going to be infinity. So what I will do is, this is probably the simplest. 1/2 P over 2 minus 1 is still positive. It's just a little smaller, 1/2. All right, so we know from calculus, or hopefully remember from calculus, e to any power, positive power times v, blows up much faster than 1 plus v to any power. Okay, so you can check very easily. L'Hopital's rule is one way to do it. That this here, well, it's never 0, and it goes to infinity as v goes to 0, because again, what's in front of the v is positive. Okay. So here, this is going to be 1/2 P over 2 minus 1 v dv. So we can say yeah, so for all v, it's positive. So it's positive. Yeah, it's positive. It goes to infinity as v goes to infinity. So it has to be bounded below by something. So let's call it m, little m. This has to be bounded below by some m for this reason. And this badly becomes infinity. What is infinity? Simply because, again, sound like a broken record, but this is key. This is positive. E to a positive times v from 0 to infinity integrates to infinity. Okay. Right. Right. So one thing to know, if you just as a sanity check, when p equals 2, this is just 1. It's e to the 0. So this is not positive. We're just simply integrating 1 over 1 plus v squared, and we computed that to be 1. So nothing, this is a sanity check when p equals 2. Okay. Okay, finally, similar thing. Sorry, 0 to yeah, I actually don't think this is going to be in LP for P between 0 and 1. But as I mentioned, at this stage in analysis, we just don't really care. Those are kind of exotic. It's almost as if books like Royden pretend like LP doesn't exist for P between 0 and 1. It does exist. I use it in my research every now and then. So, but anyway, yeah. Yeah, so we're gonna do the same thing, but as I mentioned, I'll go a lot quicker because this whole U sub thing is already done. Yeah, we're just gonna look at 1 to infinity for P between 1 and 2. Right. So 1 to infinity. x and minus p over 2 over 1 plus. I have that other problem in my head for some reason. Where was x cubed? Okay, basically same substitution. So it's going to go from 0 to infinity. I'm not going to go through all these details. But yeah, u is ln of x. When x is 1, u is 0, and x is infinity, u is infinity. So it's the exact same thing. Well, not exact same thing, but basically the same thing. 0 to infinity, e to the 1 minus p over 2 u over 1 plus sorry, this is p. Yeah, and the exact same thing is going on, really. So how did we get here before? Well, we were going from minus infinity to 0, and here what was in front of the u is a constant that was between 0 and 1, because p is bigger. Sorry, a negative constant. Yeah. This was negative, so when we did the u sub to make things clear, that made this positive when p is bigger than 2. But when p is between 1 and 2, this here by itself is positive. P is between 1 and 2, so 1 minus p over 2 is positive. And so when we're going from 0 to infinity, yeah, it's the exact same thing. This is positive. I'm not going to repeat the arguments. But, basically just break this up into 1/2, 1 minus p over 2u, 1/2, 1 minus p over 2u, like we did here. And you get this as infinity. Yeah, sorry. I don't really. Yeah, so really this p in this example, if p is just simply less than 2, then this is positive. That's absolutely trivial. This being positive is the same thing as saying p is less than 2. So p can be anything between 0, really minus infinity and 2. If p is negative, you would just simply get, this would come up into the numerator and add to the misery and make this even bigger. But yeah, p between 0 and 1 absolutely works. No different at all. Doesn't affect this denominator a bit. So yeah, so certainly f, this integral is infinity. This integral is infinity. So we're done. That's all right. I meant not in LP. Yeah. So yeah, easy counterexample. Something you just have to brand into your brain for future prelims. So, all right. Hopefully this was useful. So I'll take care.